tale of secrets and discoveries where science sets sail.
Hi and welcome to GeoCave, and welcome to this year's Vlogmas. I'm Asha, I'm a geologist living in Norway. This day's topic is Kappa, Kappa, Kappa. Let's just say, I'll just write it here, and it's a good one. Okay, yeah. We will go through Einstein's gravitational constant, the thermal conductivity, and the spring constant. So take a sip of your favorite drink and let's see what's in the cave today. Most of you, when you think of Einstein, probably think of the equation E equals mc squared, which simply states that the mass can be converted into energy and vice versa. But this is not the subject of today. Today we are going into Einstein's field equations, also called EFE. It describes how matter and energy in the universe influence the curvature of space-time. But we will just write it on the board here. We have okay, and this section here is the Einstein tensor, which represents the curvature in space-time. This letter here is the cosmological constant, and this is the metric tensor, which describes the geometry of space-time. And the last section here before Kappa is the stress energy tensor, which represents the distribution of matter and energy. And then you have Kappa here, which is Einstein's gravitational constant. Yes. Thermal conductivity is a measure of how well a material can conduct heat. Think of it as how quickly heat can travel through a material. Imagine you have a metal spoon and a wooden spoon. If you put both spoons into a pot of hot soup, the metal spoon will get hot much faster than the wooden spoon. This is because the metal has a higher thermal conductivity than wood. And it means that metal can transfer heat much more efficiently. So let's just fast write the formula here. So here you have Q, which is the heat flux, which is the rate of heat transfer per unit area. Then you have the thermal conductivity for material and the difference in temperature per distance. The temperature gradient, you might say. The spring constant is a measure of how stiff or strong a spring is. It's part of a concept called Hooke's law, which is named after the 17th century physicist Robert Hooke. Hooke's law states that the force needed to stretch or compress a spring is directly proportional to the distance you stretch or compress it. And the formula is quite easy. You have the force equals kappa times x, where the force F is the force needed used to stretch or compress it. K is the spring constant, and X is the distance. The distance you stretch or compress the spring. So there was a lot of equation today, and I thought we would just see if we, without the secret meaning, could see some connection between the three examples. And all of the examples identify some basic properties to the material they are describing. And the hidden meaning is core. Such a beautiful letter, Kappa, core. Okay, I didn't know, I had no idea. But the core is like a fundamental part of something. So, yeah. So, it kind of makes sense. But do you have any thoughts or idea? Leave a comment down below. That's me closing off for today. For more Geo-Geeky Greekness, tune in tomorrow and have a jolly day!